I don't see why that should be stopping. How's that for a snippy response? Oh, the question was asked, should we stop cutting the rough edges off of the paper? And I said, well, there's no reason why it should stop. I know it's getting to the end.
At least I don't hear Christmas songs yet.
Yeah. I've seen my first Christmas lights on the house that I passed.
And so they like Christmas music all day, every day. Once it gets time, and it gets so old.
Christmas. Well, Christmas, did you say Christmas is every day at Dillard's?
No, it's like it's Christmas music all day.
All day, every day.
Like
The whole month. I used to love it when I was a kid, but now I can't stand that stuff.
Well, it pretty much starts at Halloween now.
After. You like Christmas stuff out of Joanne?
Or just skip over it.
There are some stores that that's what they do. The
Like
Christmas.
stuff with clearance, like halfway through.
What stuff?
Fall.
Fall stuff? Okay. Wow. Yeah.
Well, like from
Yeah.
Like, so it's not even Thanksgiving.
Oh, 11:01. All right. Okay, we'll get started here. Turn in the homework 11, and then hopefully you should have homework 12. If you don't, for here I have a hard copy up here. Jenna, did you get the homework? You have it's the right pink sheet. If you didn't, I have some extra up here.
I usually get your website thing.
I like
Yeah.
this color.
Right, yeah, that's it. Do you need a copy of this, Carl? Yeah, all right. Okay. Let me put it over here. All right, so we're talking, in this whole chapter, we're talking about representing curves and surfaces, also with a different, writing them a little bit differently with, for starters, we're talking about writing them using parametric equations, which is where we introduce a third variable, and the x's and the y's are represented in terms of this third variable. So x is represented as some function of t, y is represented also by a function of t. Now, what we're going to do here is talk about a derivative then. So let's assume that y is a differentiable function of x. So that just means it has a derivative. And we're going to find out what dy dx is. Now notice the x is in terms of t and the y is in terms of t, but here we're just wanting to get the derivative of y with respect to x. So we're just going to use the chain rule here to do this. So y is a function of t. I'm sorry, y is a function of, I'm actually going the wrong way here. Let's start this out like this. Y is a function of dy dt. First of all, y is a function of x, so we can have it written as dy dx. And then to complete the chain rule, we then have x as a function of t, dx dt. So this is just from the chain rule. All right? So dy dt equals dy dx times dx dt. And of course, notice how these things appear to like cancel out from each other from the numerator and denominator. So if I divide both sides by dx dt, I get this formula here. dy dx is equal to dy dt in the numerator divided by dx dt in the denominator. Okay? And a way to remember this is that it's very simple. It's really just to think of algebra here. Basically what I've done, what you can look at it this way, is I've taken the numerator dy dt and you can just view it as dividing by dt. Because you can do like algebra stuff with these differentials. And then dx on the bottom, I'm doing the same thing. I'm dividing it by dt. So therefore, I can figure out what dy dt is and dx dt is, so I can figure out what dy dx is. Okay? Now, let's remember something from Calc 1. When we look at the derivative of a curve, the value of that derivative gives us the slope of the tangent line to the curve. So hopefully we all recall this. So let's have a little y and x axis there. Let's have some kind of curve, we'll call it f of x. And maybe this is 5. Go up to here and draw the tangent line. We know the tangent line is that straight line that just grazes the graph there. The slope of this tangent line, m, is equal to the value of the derivative at that particular value of x. So in this case, it would be equal to f prime at 5. Okay. So let me put this down here. Recall that the value of the derivative, the value of dy dx, is the slope of the tangent line. Okay. All right. So what we're going to do next here is just figure out what is the, we're going to figure out what the dy dx is at different values of t. And so we can get dy dx directly from the two parametric equations. X equals f of t, y equals g of t. All right. Okay, so let's look at a concrete example here to illustrate this. Let's have a parametric curve. Say we have a curve, we'll call it capital C, and it's defined by x equaling t squared, y equaling t to the third minus 3t. So those are our two parametric equations. So we're going to do several things involving this curve. The first one is we're going to find its derivative, dy dx. Okay, our formula is this. It's dy dt over dx dt. So let's compute those. Now be sure you put the right thing in the numerator and the denominator. dy goes on the top. So dy dt is 3t squared minus 3. And dx dt is 2 times t. All right. So basically we have dy dt then. dy dx is equal to 3t squared minus 3 over 2t. And so for different values of t, as it moves along the curve, we can then compute the value of dy dx for different values of t. So we can calculate the value of dy dx for different values of t. For different values of t. All right. So first of all, we're going to ask this, another question. What are the values of t at the point 3, 0 that's on the curve C? So 3 is our x value and 0 is our y value. In fact, before I do that, let me just show you roughly what this curve looks like here. All right. It has 3, 0 as one of its points. So our t is increasing in this direction like this. And then it keeps increasing. It hits 1, 2. It then starts to go down and hits the origin 0, 0. It then goes down to hit 1, -2. So it's going like this, it's going like this, like that. And then it goes upward again, and it recrosses that point 3, 0, and then it keeps going from there as t gets bigger. So this thing has a loop in it, and it crosses itself in one point. All right. So this 3, 0 actually has 2 values of t for where the graph crosses it. The first time we've got 1 value of t, it moves around in this loop, and the second time it crosses that point, we have a second value of t. All right. So we're going to figure out what those values are. All right. So therefore, we're talking about x. So we have x equals t squared. Here our x is equal to 3. So we're saying 3 is equal to t squared right there. So when we take the square root of both sides, we're going to have 2 values of t. T is going to be a positive square root of 3. T is going to be a negative square root of 3. All right? If we look at the y value of 0, so y is equal to t to the third minus 3t, and we plug in 0 for y, we have 0 is equal to t to the third minus 3t. Now, we can also see that those 2 values of t also solve it there. This expression right there, I can factor a t out from both of the terms. So this is equal to t times t squared minus 3 in parentheses. And there are actually 3 values of t that satisfy this, because this all is equaling our y value of 0. We've got t is equal to 0 from that first factor there. The second factor gives me those 2 values of t that I had already found, square root of 3 and negative square root of 3. So we see that these values here, square root of 3 minus square root of 3, are the 2 values of t where the curve goes over that point 3, 0. Okay, so these are the 2 common values of t. So let me go back to this graph then again. So therefore, at that particular point, we actually are going to have 2 derivatives at that point. We have one derivative for where the curve is going up this way. We have a second value of the derivative for where the curve is then going the other way. So we're going to have 2 values of the derivative. Yeah, Jenna?
Sorry, I think I made it. So it's only negative with 3 and 3. It's not 0 because it's not one of them.
Right, right. When t is equal to 0, certainly the y value is 0, but it's not in common with the 3 for the x value. Actually, if you go over here to the graph, this other point here where y is equal to 0 there, That's the other t value where t is equal to 0. Right there on that other value. Other point, rather. All right. So what we want to do next is find the two values of the two derivatives there at 3, 0. So for letter C, let's find the values of dy, dx for each of these t values. For each of these t values at 3, 0. All right. Well, we have our, we have our computation here for dy dx, so let me repeat it. It is 3t squared minus 3 all over 2t. So now I just plug in a positive square root of 3 and then a negative square root of 3. So let's plug in the positive square root of 3 here, and I get that dy dx is going to equal what? Well, it's 3t squared, but if t is the square root of 3, when I square it, I am going to get a 3 there for that t squared. Minus a 3, so that's the numerator, and then the denominator is 2 times t, which is 2 times the square root of 3. So what I get then is 9 minus 3 on top, that's a 6, over 2 square root of 3. And let's divide 2 into 6, and I get 3 over the square root of 3. So that's a perfectly fine answer, but there's a little bit simpler way that I can write 3 over the square root of 3, and what would that be? Just the square root of 3, right. Okay, so that's my value at when t is equal to a plus square root of 3, and then when t is equal to negative square root of 3, we just plug this stuff in again. My numerator is not going to change because it's t squared in the numerator, so that's still going to be 3 times 3 minus 3. My denominator, though, 2t, I'm going to have a negative in there now, so that's minus 2 times the square root of 3 there. So I get then the same numerator of 6, the denominator is minus 2 over the square root of 3, so I end up getting minus 3 over the square root of 3, which can be simplified to a minus square root of 3. Okay. So for these two, back to this graph here, for this way, when it's going this way, which of those two values would I have for the tangent line for the slope of the tangent line? Would I have the plus square root of 3 or the negative square root of 3?
Negative.
Why? It's got a negative slope, right. So this would be the negative square root of 3. Now when it rolls back around and is then going upward, it would be the positive square root of 3 slope, okay? All right, so the next question maybe we can ask on this is the following. Find the equation of the two tangent lines. All right, so we go back then to college algebra or intermediate algebra, and we use this formula here. Y minus y naught is equal to m, the slope, times x minus x naught. All right, that's a point slope formula. And basically, I know that for one of these, my slope is the square root of 3. For the other one, it's a negative square root of 3. And my y value here is a 0 for that point. My x value is a 3. So I just plug in the numbers. I get y minus 0 equals the square root of 3 times x minus 3. That would be for the positive slope. And then I would also have, and so I don't need the minus 0, of course. And then I would have y minus 0 equals negative square root of 3 times x minus minus 3 for the other tangent line, and so that would be y equals minus square root of 3 times x minus 3 in parentheses. Okay. All right. So just be familiar with, remember that point slope form from algebra. Okay. How about, let's see, another question we could ask ourselves on this is, where is the curve, where is the tangent line horizontal and where is it vertical? So find the points on curve C where the tangent line is, first of all, horizontal, and then find out where the tangent line is vertical. All right. So if we look at, just glancing at this graph again, we can tell up here, somewhere up here, we're going to have a horizontal tangent line. And then down here, we're also going to have a horizontal tangent line, okay? And finally, right here, we're at 0, 0, the tangent line there would be a vertical line. So we do have these points on the curve. Now, the way to find this out using calculus and algebra is this. Okay, dy dx is equal to, again, that dy dt over dx dt. Now, when the tangent line is horizontal, what is the slope of that line? What, in other words, more generally, what is the slope of a line that is horizontal? That's diagonal. 0, right. Slope is equal to 0 for a horizontal line. So this is our dy dx, which is what we're using to figure out the slope. So when we have something with a numerator and a denominator, and we're trying to figure out where it equals 0, we look to the numerator, okay? We look to find where dy dt is equal to 0. And at the same time, we hope that the denominator doesn't go to 0 also. So we hope that dx dt doesn't equal 0 at that point. So does everybody see that's where we're going to look for horizontal, for 0. So we know the formula for dy dt, that's that 3t squared minus 3, all right? So, and we want to set it equal to 0 and solve it. Oh, thank you, minus 3t, yep. Is it minus 3t? I forgot. Where are we? No, it's just minus 3, isn't it? Because it started out, it had minus 3t in the original, so it's 3t squared minus 3. All right. So anyway, so we just solved this, equal to 0. Well, simple thing, 3t squared, add 3 to both sides, divide 3, so we got t squared is equal to 1. When we do the square root, we find out that t is equal to a positive 1 and a negative 1. All right. So those are the two values. And then at those values, let's look at dx dt. dx dt is represented by the formula 2t. We're okay because when we plug in plus or minus 1, we don't get a 0 for the denominator. All right. Okay, so these are our two values of t. Where the tangent line is horizontal. So how can I find the corresponding x and y coordinates for those two values of t? Exactly. go back to our original parametric equations, x equals t squared, y is equal to t to the third minus 3t, and plug in each t value there. So we just plug in to the parametric equations. And we find out that, so when t is equal to 1, we do the arithmetic. We have, let's see, when t is equal to 1, what is it? It's x is t squared. So x is equal to t squared, so x is equal to 1. Y is equal to t to the third minus 3t. So therefore, when we plug in 1, we get negative 2. So 1 comma negative 2 is the 1 point, and then when we do t is equal to negative 1, do the same process. We again get 1 for x, but this time we get 2 for the y value. And then if we look up here at our curve here, this point at the top is 1 comma 2. This point at the bottom is 1 comma negative 2, where the tangent line is horizontal. And then the other question here is where the tangent line is vertical. Okay, for this, we're talking about looking where basically the slope is really infinity. Okay, for a vertical tangent line, if we can talk about a slope being equal to infinity, that's what it would have to be. Okay, so we're really saying m is equal to infinity here. Now, again, our dy dx is dy dt over dx dt. So for that to equal infinity, we want to look to see where the denominator is equal to 0. All right? So get denominator dx dt equal to 0. All right? And hope that the numerator isn't also 0. And hope that the numerator doesn't also become 0. So dx dt, then, we figured out that is the 2t. So we set that equal to 0, and the only solution, of course, is t equaling 0. And that value of t does not cause my numerator to be 0, dy dt. So I'm okay there. So that's my t value. So the corresponding x and y value, when I plug in t in 0 into the parametric equation, well, for t squared, that's going to be 0 squared. And for 3t squared minus, what is it, for t cubed, rather, minus 3t, that's going to be also 0. So the point that I get is the origin 0, 0 for my x and y values when t is equal to 0. And that's exactly what we see here on this graph here. That origin, that's where the tangent line would be vertical. Okay. Okay, so we've looked at computing the derivative, looking at where the tangent line might be horizontal or vertical. All right. Let me do one more thing with this curve, and this might be a concept that is not particularly jumping to mind from Calc 1. Let's look at this. Do you guys remember the phrase concave up and concave down? Okay. Let me just look at a curve here. Is this curve, is that curve concave up or concave down? Up. Okay, it's concave up. And this curve would be concave down, all right? Okay, so did you learn some kind of little crazy little phrase to remember that?
Both points are pointing up.
Both points are pointing up. Okay, I think I've heard something like, what is this? Milk in a cup. Something, milk stays in the cup when it's concave up. That kind of thinking. Nobody's ever heard anything somewhat like that. Okay, so maybe it's something I dreamt. All right. When I teach the survey calculus class, this is what I use to try to teach this is my smiley and unhappy face. All right, and this is the pluses and minuses here are the second derivative sign, second derivative positive, second derivative negative, and of course this smiling mouth is a concave up curve, and this frown mouth is a concave down curve. So, but another thing that to remember with concave up and concave down is that when the curve is concave up, the second derivative is greater than 0. When it's concave down, the second derivative is less than 0. All right. So this is, I think it's helped some students, at least in that class, to kind of remember the difference. All right. All right. So the last thing then to talk about here with this, to get back to this curve, is this F. Where is the curve C concave up, and where is it concave down? All right, and for that we have to look at the second derivative, as I just said. So I'm going to abbreviate concave up as CU, and so that's when the second derivative, d squared y dx squared, is bigger than 0. Concave down, second derivative, less than 0. So the question arises, okay, we're given two parametric equations for x and y. How do we figure out this second derivative? How do we figure out d squared y dx squared? All right. Well, this is the fact here for this. Fact. Second derivative d squared y dx squared is equal to this. It's equal to the derivative of the dy dt that's in the numerator over just plain dx dt. All right. So this is something you may want to keep in mind. Let me put a couple asterisks there by that. So this is the formula. Notice we don't take the derivative of the bottom part, dx dt, but we do take the derivative of the top part, dy dt. So in this case, in our case here, we figured out that we had dy dt, where is that at here? Dy dt was 3t squared minus 3. So therefore, I have to take its derivative again to get the numerator, and that's going to be 9t, and the minus 3 goes away. Oh, that goes away. Hold it. Wait a minute. Something seems wrong here with this. All right. Let's do this again. I apologize. This is the following. This is the derivative of dy dx. Okay, that's what this is. And so what this is then is I do this formula again where I have this derivative respect to x, so I do the denominator is still dx dt. But the top part here is the derivative with respect to t of dy dx. I'm so sorry, I messed that up. Okay, so second derivative is the derivative of our first derivative. I'm going to again divide both top and bottom by dt. So I've got the dx dt on the bottom, and on the top I have the derivative of dy dx, and then I have the dt. All right. So let's put an asterisk there. All right, so therefore, what do we get here for the top? We found out that dy dx is equal to, where did we get that? 3t squared, equal to 3t squared minus 3 all over 2t. All right, we found that out. So therefore, for the numerator, I need to do the derivative of this with respect to t. Now, there's an easy and a hard way to do this. If I've got two terms in the numerator and only one in the denominator, what's one way I could do to get this derivative again with respect to t, rather than maybe going through and doing the quotient rule? Split it up, right. So I have 3t squared over 2t for my first term, and minus 3 over 2t for my second term. And the first term I can cancel out a t, so I have 3t over 2 for my first term, and minus 3 over 2t then again for my second term. Okay, so I do this derivative here on the top, and I get the 3 over 2t becomes 3 over 2. This is a t to the minus 1 power. When I do the power rule with this, I'll get 3 over 2t squared when I put the t back in the denominator. That's my numerator. My denominator is just dx dt, and that's just 2t. All right. Okay. So, okay. Now, what we want to do here is figure out where this is. Where is it greater than 0? Where is it less than 0? Right. The top part, let's just look at the numerators here. 3 halves plus 3 over 2t squared. If that numerator, no matter what my t value is going to be, is that ever going to be negative? No. That numerator is really nice. It always stays positive no matter what my t value is. So therefore, the only thing that the changing of the sign is going to depend on is the denominator 2t. So when t is negative, I'm going to have a negative second derivative because the denominator will be negative. When t is positive, I'll have a positive second derivative because the denominator will be positive. So therefore, it's greater than 0 when t is bigger than 0. It's less than 0 when t is less than 0. So I can say here for the final answer on this, it's concave up when the t is bigger than 0, and it's concave down when the t is less than 0. All right. And if we look here at this curve, this whole part of the curve right here, where it's going down, this is the concave down part. T is actually still less than 0 there. And then here t is equal to 0. And for this part of the curve, it's a concave up curve. As far as homework is concerned, we're not going to get too hung up on, at least on this section, on concave up and concave down. But I thought I would just throw it in there to kind of just remind you guys, refresh your memories as to what those two terms mean. All right. This other kind of example that I want to do here is actually what I want to do next here is, Okay, we looked at how to get the derivative dy dx. So we found dy dx, all right? And what we're going to look at next is arc length. Okay. Now, let's recall from chapter 8, I believe, what the arc length is. We'll call it capital L, and that can be represented one of two ways. X from A to B of the square root of 1 plus dy dx squared dx. And this is if the curve, the length of the curve as x goes from A to B. And we could do it the other way if the curve is defined in terms of y, or the arc length is the integral from C to D of 1 plus dx dy squared dy, and that's the length as y goes from C to D. And by the way, just FYI, those are two formulas that you need to keep in mind for the next test. All right. Now, how to get arc length if it's a parameterized curve. So how can we get arc length? If the curve is described by x equals f of t, and y is equal to g of t, right? Well, it's very similar. Again, the length, the arc length is an integral. Now, I'm going to use alpha and beta for our endpoints, and this alpha and beta, this is the t values that this curve is going through. So this is as t goes from the value alpha to the value beta, all right? So we have the antiderivative alpha beta, and then again it's the square root, but this time it's going to be dx dt in parentheses squared plus dy dt in parentheses squared dt. Again, let me put an asterisk there by that formula for arc length if the curve is parameterized. And this is true. This equals the length as long as the curve is traveled only once. Traveled only once as t goes from alpha to beta. In other words, it doesn't circle around again, just one time. Yeah, Jenna? Parameter. That t, that extra variable t that we're introducing here, that is called the parameter. So these are called parametric equations for the x and the y. All right, so let's look at, we'll have time, I think, to do one simple example here of arc length before the class closes. Let's do this one example, and we'll continue up with this on Wednesday. So here, find the arc length of the curve defined by x equal cosine of t, y is equal to the sine of t, and here we have t going from 0 to the value pi. No, 2 pi. Okay. Now, if you're alert enough, you realize that this is really a circle going all the way around from 0 to 2 pi. Let me just show this. This is the unit circle. Here's t. It starts out. It's going to go around like this. Keep going around, around, and around. unit circle. Okay. So what is and this has radius 1. So what is the circumference of a circle with radius 1? 2 pi, right. Right. So we know our answer is going to be 2 pi. Let's see if that indeed is what we get here. Okay, our arc length is equal to integral 0 to 2 pi. And then, well, wait a minute, we got to figure out what dx dt is and what dy dt. The derivative of the cosine is the negative sine, so that's minus sine of t, and dy dt, derivative of the sine, is the cosine of t, all right? So let's plug that into our formula here, and we're going to have minus sine of t squared plus cosine of t squared dt from our formula. And what is this going to equal? 0 to 2 pi square root of sine squared of t plus cosine squared of t dt. So what's the value under the radical? 1. Right. So this is just the integral from 0 to 2 pi, oops, let me put a little other leg there, of 1 dt. So the antiderivative of 1 dt is t, right? From 0 to 2 pi. And so the value there is 2 pi minus 0, which is exactly what we would know it to be from geometry, okay? So this is a simple example, very, very simple example of getting the arc length. We'll start out the next time with a more realistic example to get arc length. And then the next thing we're going to do after that then is surface area when we revolve it around an axis. Yeah, Jen?
So arc length is the same as the radius.
Arc length is the same as the radius? What are you saying now? Okay, now, arc length, let me tell you, arc length is the length of the curve. Have you watched the video yet? A lecture? On Friday? Huh? Were you here on Friday? Okay, and what arc length is the length of the curve?
That's what I thought, but then I thought you said when we were talking about the unit circle, that the r was equal to 2 pi, that's what we just
No, I didn't say r is equal to 2. At least if I did, I hope I didn't say that. The radius of a unit circle is 1. What's the circumference of a circle is 2 pi r, which is 2 pi times 1. Right, okay. All right, so we'll continue with this then the next time and talk about